All right, so we're going to go ahead and go over the root tests to wrap up our lesson from 11-6. And there are a lot of similarities in comparing the root test to the ratio test that we looked at earlier in this lesson. Okay, so the root test says to suppose we have the series a sub n, and then we're going to define the limit as n goes to infinity of the nth root of the absolute value of a sub n, which we can also think of rewriting that as the limit as n goes to infinity of the absolute value of a sub n raised to the 1 over n power. We're going to say that that limit is equal to L. Okay, so then there are three possible outcomes just like we had with the ratio test. So if the limit L is less than 1, that tells us that the series is absolutely convergent and therefore convergent. If L is, that should be greater than 1. So if L is greater than 1, the series diverges. And if L is equal to 1, that's worst case scenario for you guys, which means that the test is inconclusive. So the work that you used with the root test there was for nothing because you have to use another test to determine if the series converges or diverges. Okay, so again, your three possible outcomes are exactly the same as with the ratio test. Now, there is a limit that you run into quite frequently when using the root test, and that's going to be the limit, excuse me, as n goes to infinity of n raised to the 1 over n power, and that limit is going to be equal to 1. Okay, so let's take a look at like why that limit is going to be what it is. Okay, so let's say, for example, we set y equal to n raised to the 1 over n power. And we want to take the limit as n goes to infinity of that equation. So I'm going to apply the limit as n goes to infinity to both sides. So we're going to take the limit as n goes to infinity of y, and that's going to be equal to the limit as n goes to infinity of n raised to the 1 over n power. Okay, and what I'm going to do here is, so I'm going to do this work over on the side. All right, I am going to, for me to like evaluate the limit on the right hand side, you have essentially as n gets big, you have infinity raised to the 0 power, which is an indeterminate form. So what we're going to do here is we're going to apply the natural log to both sides of the equation. All right, so on the left-hand side, we get the limit as n goes to infinity of the natural log of y. And on the right-hand side, we're going to take the limit as n goes to infinity of the natural log of n raised to the 1 over n power. And once I take the natural log on the right-hand side, I can go ahead and pull 1 over n out front as a factor. So I'm going to go ahead and erase that and pull 1 over n out front. And if I pull 1 over n out front, essentially on the right-hand side, what I have is the limit as n goes to infinity of, I can rewrite the right-hand side as the natural log of n divided by n. Okay, which as n gets large, both the numerator and denominator go to infinity. So that's a candidate for L'Hopital's rule, which gives me the limit as n goes to infinity of the derivative of the numerator is 1 over n. The derivative of the denominator is 1. And as n gets big, that goes to 0. Okay, now there's nowhere for me to use the limit on the left-hand side. So the limit as n goes to infinity of the natural log of y is just the natural log of y. So that's going to make the natural log of y equal to 0. And that occurs when y is going to be equal to 1. Okay, that then shows that that limit does in fact, so the limit is n goes to infinity of n raised to the 1 over n power. That limit does in fact go to 1. Okay, so that's how we like mathematically establish that that limit is in fact equal to 1. Okay, so let's do a couple of examples here utilizing the root test. Okay, so the directions ask us to determine if the series converges or diverges. And like, what are some good situations where we can use the root test? When you look at the numerator for number 1, when you have n raised to the n power, like, you're not going to be able to use ratio test for that because it's going to be hard to compare like n plus 1 raised to the n plus 1 power to n raised to the n power. Okay, so when you have n raised to the power of n, then that's usually a good sign for you to use the root test. Also, when I look at the denominator, both the numerator and denominator have exponents, like exponential expressions involving n. So when I take the nth root of the absolute value of that formula, that's usually going to work to like eliminate some of the n's in the exponent. Okay, so let's take a look at using the root test here. So when we take the limit as n goes to infinity of the absolute value of a sub n, which is n raised to the n power, over 3 raised to the 1 plus 2n power, and then we're going to raise that to the 1 over n power. It's the same thing as taking the nth root of that expression. Okay, so we want to go through and simplify this expression now. Okay, so we have the limit as n goes to infinity. Now, when we have a power raised to a power, algebraically we multiply the exponents in that instance. Okay, so that's going to make the numerator, when I apply the exponent of 1 over n to the numerator, that's going to make the numerator become n raised to the first power. And then on bottom, when I distribute the exponent 1 over n across both of those terms in the power in the denominator, we get 3 raised to the 1 over n power plus 2. Okay, so as n gets big, that numerator is going to go to infinity. And the denominator, 3 raised to the 1 over n power, as n gets big, 1 over n goes to 0. And then so our denominator winds up becoming 3 to the 0 plus 2 power, which is 3 squared, which is 9. And infinity divided by 9 is infinity. And since that is larger than 1, we can therefore say that the series diverges by the root test. Okay, so that's how we can utilize the root test to show convergence or divergence for that series. All right, when we look at number 2, for number 2, we have the sum from 0 to infinity of the quantity 5n minus 3n cubed divided by 7n cubed plus 2, and we're raising that entire fraction to the n power. Okay, so you should be able to look at that and tell, okay, root test is definitely going to be a good one to use here because when I take the limit as n goes to infinity of the absolute value of a sub n, okay, which is going to be 5n minus 3n cubed over 7n cubed plus 2 raised to the n power. And then I'm going to raise that formula a sub n to the 1 over n power. These two exponents here, n and 1 over n, are going to cancel out and become 1. Okay, so this then becomes the limit as n goes to infinity of the absolute value of 5n minus 3n cubed over 7n cubed plus 2. The end behavior of the numerator is negative 3n cubed. The end behavior of the denominator is 7n cubed. So that's going to simplify to the absolute value of negative 3 over 7, which is 3 over 7. And since that is less than 1, since that limit is less than 1, we can therefore say that the series absolutely converges by the root test. Okay, so I think like example 1 and example 2 like illustrate the like two most common types of formulas for a series where utilizing the root test is the best choice. Okay, I want to see you guys do the root test for number 3. So for number 3, you have the sum from 3 to infinity of negative 12 raised to the n power divided by n. All right, so go ahead and pause the video. Use the root test for this to determine if that series converges or diverges, and then turn the video back on and I'll go through the solution to this. All right, so for 3 here, we're going to take the limit as n goes to infinity of the absolute value of our formula, so negative 12 raised to the n power divided by n. And then we're going to raise the absolute value of our formula to the 1 over n power. Okay, so in doing so, this becomes the limit as n goes to infinity of, when I apply that exponent to the numerator, we get negative 12 to the n times 1 over n power, which is negative 12 to the first power. And then we're going to divide that by n raised to the 1 over n power. Okay, so as n goes to infinity, we said that our denominator, n raised to the 1 over n power, okay, we set up here that that limit was going to be equal to 1. So then this becomes the absolute value of negative 12 divided by 1, which makes that limit 12. Okay, and since that limit 12 is larger than 1, we can therefore say that the series diverges by the root test. Okay, so again, the root test, like the conclusion of the root test is exactly the same as the ratio test. It's just the way we conduct the ratio test and the root tests are going to be different. All right, so that's it. That is our last series test. And then in class on Thursday and Friday, we're going to take a look at some strategies for like figuring out what tests to use to show convergence or divergence for a given series. Okay, so hope you guys have a great rest of your day. We'll see you guys in class on Thursday and Friday. Take care.